So we've been looking at some shortcuts for calculating the derivative of a given function for different types of functions. And when we do that, we always come back to the definition of the derivative. So we have two more classes of functions we want to look at today. First of all, if you have two functions multiplied together, is there a pattern for what the derivative would be for two functions multiplied together? And as you're going to see, it's not what you might expect. It's not the derivative of the first times the derivative of the second. So let's apply our definition of the derivative. This is our big function f of x together. And so the derivative of that would be big F of x plus h minus big F of x all over h. So our job now is to reorganize this into something that's recognizable but becomes simpler. Now what we're going to do with this won't seem immediately obvious, I'm sure, but what we're going to do is we're going to add and subtract into the numerator of this line f of x plus h times g of x. So in this line down here, I have subtracted and added this quantity into my line from here. So I haven't changed anything. If I subtract and add the same thing, it looks different, but the value of the numerator is still the same. So of course the question is now, so why did we do that? So what I'm going to do is, out of these first two terms, I'm going to factor out f of x plus h, and that's going to leave me with g of x plus h minus g of x. And because I'm doing the limit of a product, I can break that up as follows. Similarly over here, I can factor g of x out of both parts. So I have the limit of h approaching 0 of g of x times what's left over, f of x plus h minus f of x. And as I do my limit, as h goes to 0, this will go to f of x. This you will recognize as the derivative of g, so g prime of x. Next, h approaching 0 of g of x would just be g of x. And this last piece, the limit of h going to 0 of this, would be f prime of x. In other words, we've shown that the derivative of f multiplied by g is f times g prime plus g times f prime. Or the way I like to remember it is the derivative of f times g is the first function times the derivative of the second plus the second function times the derivative of the first. Alright, so here's a simple example of how I could use the product rule. I have a function here made up of two functions multiplied together, f and g. So if I want to do the derivative of the overall function with respect to x, it's going to be the first function times the derivative of the second plus the second function times the derivative of the first. Or x squared plus 3 times the derivative of 4x squared minus 3x plus 2 plus the second function times the derivative of x squared plus 3. And now to do each of these sections, I'm going to use other rules I know. I know how to do the derivative of the sum and difference with the power rule embedded. So my derivative y prime would be x squared plus 3 times 8x minus 3, derivative of 2 is 0, plus this function multiplied by the derivative of this, which would be 2x plus 0. And there's no need to expand it out. My derivative is simply that. Alright, now similarly the derivative for a quotient of two functions could be developed using the definition of the derivative, and I'm not going to do that just because it's time consuming, and I just want you to get the idea that all of these rules come from the definition of the derivative, and I've proven quite a few of them already. So I'm just going to tell you what the derivative of a quotient would be. If you're interested in the proof, you can always just look in your textbook. If you have f divided by g, the derivative will be g times f prime minus f times g prime, all divided by the bottom function squared. Okay, so it turns out to be the bottom function times the derivative of the top minus the top times the derivative of the bottom, all divided by the denominator squared. Alright, so just applying this to a given situation, the derivative of two functions divided would be the bottom function times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator squared. Alright, so we're going to have 2x plus 1 times a power rule, which will be 2x minus x squared times the derivative of this sum, which would be 2 plus 0, so just 2, all divided by the denominator squared. And let's just clean up the top a little bit. We could multiply and so the derivative would be 2x squared plus 2x all over 2x plus 1 squared. And I could factor the numerator, but there's no need to because nothing is going to cancel on the denominator. And so the derivative of my given quotient is this. Now just one last miscellaneous thing I want to throw into this, and that's about higher order derivatives. We've talked all about the first derivative, the rate of change. And the notations are any one of these three, y prime equals f prime of x equals dy dx. But we can take derivatives consecutively as long as we want, as long as the function continues to be differentiable. So the second derivative notation is shown here. Third derivative. And then once we get past third derivatives, if we get into fourth derivatives, then we, instead of putting the slashes, we just put a 4 in brackets, so fourth degree. So if you were asked to find the third derivative at x equals 1, then you simply apply the derivative consecutively using the rules we've talked about. So if you're given y equals 4x to the 6th, the first derivative, this would just be a simple power rule. 24x to the 5th is the first derivative. The second derivative, apply the power rule again. 120x to the 4th. The third derivative, 480x cubed, and then we're being asked to calculate the derivative, the third derivative, when x is 1. So plugging in the specific point, we get 480.